Lesson 26, guess what? We are learning 4 derivatives. Okay, so we pretty much know just how to take a basic derivative of a power. Okay, so we know that step. Yesterday, we dealt with the cases when there's a coefficient in front or if you have multiple terms being added or subtracted. Today, we're going to learn some special derivatives where it's not a rule, such as moving the power out front, subtracting 1 from the power, but it's just one you have to memorize. Okay, so as we go through these, there are derivatives you just have to flat out memorize. Okay, the first 2, we're looking at the top half. First of all, the derivative of e to the x. So this is specific, e to the x. Derivative of e to the x is e to the x.
Simple.
It is very simple. The derivative of e to the x is itself. It does not change. Okay? The other one we're going to look at here is the derivative of the natural log of x. Now, officially they have absolute value here just because a number in a log has to be positive. So it's the natural log of x, and the derivative of the natural log of x is 1 over x. Okay? Again, just derivatives you need to flat out memorize.
That wasn't so bad.
Okay, let's practice with them. Okay, and so these practice problems, you'll see we're going to still use our previous rules. We're adding these new derivatives, putting it all together. So, find dy dx, find the derivative, given that y equals 4 natural log x minus 6 e to the x plus 2x squared.
Wait, is this like what we did yesterday? We just split it up into 3?
Yes. So we have 3 things we're finding the derivative of, 3 pieces. So, dy dx. So derivative of 4 ln x. Well, did we just learn a rule for the derivative of ln x?
Yep, we did.
Okay. What is the derivative of the natural log of x? 1 over x. Okay. Whether they have the absolute value there or not, you still say 1 over x. What about this 4 in front? It just times by it. So for right now, for this first step through, I'm going to write it as 4 times 1 over x because it's a constant 4. It's still there. The derivative of the natural log of x is 1 over x. And so, okay, we'll clean that up in a moment. Derivative of minus 6 e to the x. Hello? He's good? Okay. Okay, good deal. Okay, bye. Okay. You're good. Yeah. She said, tell Riley he's good, so.
When she said that, I was like, oh, I probably actually did fail it. And then I was like,
And I can't remember. I thought I remembered you had, at least in math. I wasn't sure about English. I don't know that, but okay.
that'd be pretty sad if I was in calc.
And thus her question, why are you in calc then? Or how are you in calc? Okay, minus 6e to the x. Derivative of minus 6e to the x. Exactly that. Because the minus 6 is just a constant. You carry that down. What is the derivative of e to the x? E to the x. Plus derivative of 2x squared.
That's easy.
Going back and using our previous rules, right? Bring that 2 out front and multiply. 2 times 2 is 4. X to the 2 minus 1, which is 1. Okay, that is it, other than I'm going to do a little bit of cleanup. 4 times 1 over x. How could that be written? 4 over x. Minus 6 times e to the x is 6e to the x plus 4x. Questions? Example 2 then.
Wait, don't we need an X on
Yes.
Okay, to make sure, I was like, I thought we had
What did you say, Wade?
the 4.
I had failed to write the X on my 4. I don't know if I said it. I feel like I said it
Yeah,
maybe,
you said
but
it.
just didn't write it.
So I was looking ahead at the next problem, then I just looked up like,
Yeah.
I thought he said, do we need to axe it? And I was like,
Okay.
Do an axing in here.
Okay. Example 2. Find dy dx given that y equals 4 natural log of absolute value of x minus 6 e to the x plus 2x squared. So what's different about this problem?
that's the absolute value. Literally,
Right. In terms of derivatives, it doesn't matter. All this is saying absolute value is it is specifying only positive values. That's what it's specifying that of x. So in this case, x could actually be a negative on this one because when you put the x in, the absolute value is there. But does it change anything when I take the derivative? No, and that's kind of the point of this problem. So, dy dx, 4 natural log x. What's the derivative of 4 natural log of x? 4 over x. Because you keep the 4. Derivative of natural log of x is 1 over x. So if it's 4 times 1 over x, that is 4 over x. Minus derivative of 6e to the x. 6e to the x stays the same. Derivative of 2x squared. 2 times 2 is 4. Subtract the 1, 4x. Okay to move on? So derivative of e to the x is e to the x. Derivative of natural log of x. 1 over x. Okay, we got 2 others to learn. The derivative of sine x. The derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. So they're almost each other's derivatives, except when you do the derivative of cosine, it is negative sine. Okay?
You know why that is?
It has to do with the direction of the curve. I'd have to think it through. Okay. Find the derivative of y equals 3 sine x minus cosine x plus 2 e to the x. Okay, derivative of 3 sine x. The 3 is going to stay a constant of 3. What's the derivative of sine x? Cosine x. Okay. Minus, what's the derivative of cosine x? Negative sine x. So that's it. For the moment, I have it written as minus negative sine x. I'll fix that in a moment. Plus, what's the derivative of 2e to the x? 2e to the x. E to the x stays as is. So if I clean this up a little bit, 3 times cosine x is 3 cosine x minus a negative sine x is plus sine x plus 2e to the x.
So I'm kind of confused. Couldn't we just, because it starts as sine, it goes to cosine, but if you were to do it again, it'd turn it into a negative sign. Can you only do it once?
You can do, and we haven't talked about higher order derivatives. You can take the derivative as many times as you want, but that doesn't mean it'll take you back to the original.
Yeah, so it's like, I don't know how sine and negative sine would teach you the same answer.
No. Actually, with your sines and cosines, I think it takes you a rotation of 4 to take you back to the original. So,
that is the only right answer, though?
yes.
Okay.
Yep. You just take the derivative once, and then you're done.
Okay.
Yes.
So I don't know what the rule is for it, so that's why I'm asking. For the 2e to the x, would you ever take the x and put it in front of the 2?
No.
Okay.
No. That, when you move the power in front, only works when the base is the variable.
Oh, okay.
It doesn't work when the x is in the exponent. Okay, so, and this rule is specific to base e to the x. Later on this year, I feel like it's a much later down the road, we'll learn how to take the derivative of something like 2 to the x. So when you have a number other than e in your base, there's a specific rule of derivatives like 2 to the x, 3 to the x, so on and so forth.
Okay.
But the very first rule we learned is specific to when your base is a variable. Okay?
Yeah, I wasn't sure because there was the 3 in front of the cosine x, but then the other x was there. So.
Okay. One more example here. Find the derivative of y equals negative 3 cosine x plus 3 natural log x minus 2 sine x. So dy dx. Derivative of negative 3 cosine x. So for the brief moment, and if you're already there, that's fine, I'm going to consider it as the negative 3 stays negative 3. And then what's the derivative of cosine x? Negative sine x. So officially, when you multiply negative 3 and negative sine, that becomes positive 3 sine x. So just realizing when you take the derivative of cosine, that will change the sign on whatever you're doing. Okay? Plus derivative of 3 natural log of x. The 3 stays a 3. What's the derivative of natural log of x? 1 over x. And so when you multiply 3 times 1 over x, that becomes,
3 over x.
or just 3 over x?
Yeah.
Okay. Minus the derivative of 2 sine x. So the minus 2 I'm going to keep. What's the derivative of sine x? Cosine x. And so this part is just minus 2 cosine x. Okay? All I can say is memorize those rules. Flat out know them. Okay? Because we will add more derivatives, right? Okay, derivatives is kind of a building process all year long. Okay, we're learning the basics. We'll learn a little bit more. We'll keep going with it every time. Okay, I do want to look at one example of exponential growth and decay. We have this, what's the word I want to say, trend all year long, where we look at a variety of problems like this. So, exponential functions are of the form a of t equals a sub naught, or a of o, times e to the kt. Okay, where t, as always, stands for time. A sub 0, have you, in science, you guys call this a naught?
Yeah.
Okay, a naught, the original amount. A of t is the amount at time t, and k is your growth constant. Kind of like when we have direct and indirect variation, k is a constant. Now, when we see these types of problems, notice it says we usually have to solve for k before we can solve for what they're asking for. So kind of like the variations, the indirect and direct variations, before you actually do the problem, we find k first. So, I'm going to go ahead. The base of this problem is a of t equals a sub naught e to the kt. I haven't read the problem yet, but I'm just writing that down. So, the number of bacteria present at noon was 400, and 9 hours later, the bacteria numbered 800. Assume exponential growth and find an equation that describes the number of bacteria as a function of time t, where t is measured in hours. Then find the number of bacteria present at noon the next day. Reread it a couple more times if you need to, right? Let's go through and identify some pieces here. What kind of pieces do you know? Okay, A of O is 400 because that's the initial amount they give me, right? Yes, it's present at noon, but that's just when it happens to be. Okay, so A of naught, A sub O is 400. What about 9 hours later? That's your time, that's your T. And do pay attention to the fact it is in hours. 9 hours later, the bacteria numbered 800. What is that? That's A of T, because that is the amount at time T. So at 9 hours, when T is 9, then A is 800. So that is what we will use for A of T. Assume exponential growth and find an equation that describes the number of bacteria. So, fill in what you know, guys. A of T. So at time T, at 9 hours, this is 800. A of 0, 400. E is E, that's a number, yes. K is what we're going to first have to find out. And T is 9. So notice I have all variables filled in with the exception of K. That means my job is to find K. How do I get that E by itself? Okay, so your first job is to get this E in its power by itself. So if it's 400 times this, we're going to divide by 400. If we divide one side by 400, divide the other side by 400. 800 divided by 400 is 2. The 400 divided by 400 cancels to be 1, and I'm left with E to the K times 9, or I'm going to say 9K. I just like that better. Okay, so this comes back to our equation solving rules. How do we solve for K when it's in the exponent and we have a base of E? We take the natural log of both sides. So the natural log of 2, I'm going to write as the natural log of 2. Over here, for the moment, I'll write it as the natural log of E to the 9K. Do you remember how this works? Yeah, on this one, when it's natural log of E to the 9K, natural log is base E, and this is base. So because these E's are the same, natural log of E to the 9K is just equal to 9K. And so on the right, 9K. On the left, we still have natural log of 2. How do I solve for K? Divide by 9. And so K is natural log of 2 over 9. You can go the decimal route if you want. We'll need our calculators at some point. I'm not going to write it as a decimal right now. Okay, I'm going to just write it as natural log of 2 divided by 9. Or if you wanted, you could write it as 1/9 times the natural log of 2. I've seen that done too. Okay, my job was to write an equation. Do I have the knowledge to write an equation now? Yeah, okay. When I'm writing this equation, A of T is just going to be A of T, because that 800 was specific to time 9, right? So I'm not writing the equation for a specific, I'm just writing a general equation. So A of T, A naught. That's always going to be 400, right? That's your initial amount. That's not going to change. And then it's E to the KT. Well, my K is natural log of 2 divided by 9, and then times T. And this is where it might be better a little bit to say 1/9 natural log of 2 times T, but
I didn't know if we put 24 instead of T since it's been already.
no, because right now I'm just writing a generic equation that I can fill in for any time.
Oh, okay.
Okay, so this right here answers the part of find an equation that describes the number of bacteria as a function of time T when T is measured in hours. Now I'm ready to go on to the last sentence, which says, then find the number of bacteria present at noon the next day. What does noon the next day tell me?
24 hours.
24 hours, right? Because my A naught, my 400 was at noon the previous day. So we're going to be trying to find A of 24. And that's because we're using 24 because it specifically said T is in hours. If T was in days, then I just use T as 1. So 400, E to the natural log of 2 divided by 9 times 24. I don't know about you, but I've hit a definite calculator point. So 400 E to the natural log 2 over 9 times 24. Not the best notation. Probably should have changed that notation, but if you've entered it a correct way in your calculator, your answer should match my answer.
Yes.
2539.
Oh, I know why I put 44 instead of 400.
I don't
Yeah.
do it.
Enter your calculator pieces carefully, right? So yeah, mine is 2539.841683, which, if it specifically says find the number of bacteria, in terms of whole numbers, that is approximately 2,540 bacteria. Okay. Work with those exponent problems, those growth and decay, because you will see those at varying levels throughout the year. Okay, so that's not just going to be we do it once and then we're done. There will be a continued trend there. What's the derivative of e to the x? E to the x. What's the derivative of sine of x? Cosine of x. What's the derivative of cosine? Negative sine. And what's the derivative of natural log of x? 1 over x.
I was waiting for you to say that one.